Hello all. Welcome to the September meeting for the North America Research Interest Group. I'm very happy to have you with us today. We've got a couple of great talks in this meeting. The first talk is a project from the Red Hat Collaboratory Boston University. Our speaker will be Vasia, Kalavri, who is an assistant professor in the computer science department at BU. Vasia will be talking about temporal graph analytics on Apache Flink Stateful Functions. Our second talk will be given by Ashlyn Knox on the Fedora website Revamp. Ashlyn is a developer with the Fedora websites and apps team, a UI designer and UX researcher with the Fedora design team, a web development instructor at SAIT, which is the southern side. Sorry? I thought I mispronounced that. Southern Alberta Institute of Technology. And while most of her work focuses on front-end development, she has full-stack experience and specializes in JAMstack site architecture. So with that, I'll hand it over to Vasia to kick things off.
Great. Thank you very much for the great introduction. It's very nice to be here today to share our ongoing work on a temporal graph analytics library that we have been building on top of Apache Flink Stateful Functions. And as Ahmed already mentioned, this is funded by Red Hat Collaboratory here at BU. So we have been using graphs to model the world around us literally for hundreds of years. So graphs help us model relationships, interactions, dependencies between entities, and we can analyze them to gain insights into all kinds of things, like people's interests and behaviors, to build efficient transportation services, to power search engines, develop recommendation systems, and so on. Or to give you a more relevant use case that you may care about, graphs can also help us understand and optimize the performance of large-scale distributed systems. So in this slide, I have an example graph of a microservices architecture of a social network application. And we can use a graph to understand how the services communicate with each other, right? If we represent the services as vertices in this graph and communications as edges. So if we analyze this graph, we could get insights about how the services interact with each other. For instance, one could ask a query like, which services are reachable from a particular service, like, for example, the user timeline. But we may also be interested in asking queries that would help us understand the behavior of this deployment over time. For example, an operations engineer might be interested in knowing which services are frequently on the critical path of requests. Or maybe they're debugging some incident, maybe an SLA violation, and they want to extract request paths that contributed to increased latency around the time when this violation happened. Or we might be interested in monitoring in a continuous way some critical services and make sure that they are always reachable, that they're never disconnected from this graph. These last three queries, we call them temporal, and because they look at the evolution of the graph over time. They don't look at a specific snapshot, but they analyze how this graph changes over time. So we can model real-world graphs as edge events, which we call streams. And all of these examples that I gave before can be modeled as such edge activities with timestamps. For example, a purchase online is an edge that is being added to a graph, or a movie rating, or a like on a post, a transaction, or a message sent from one microservice to another could be represented as an edge in a continuously evolving graph. So this project is about storing, managing, and analyzing these types of graphs that we call temporal. And this is a very interesting type of workload from a systems perspective because it presents very unique challenges for system designers. So at this point in time, if a user wishes to perform streaming analytics on such a temporal graph, they have a few options. One of them is to use a graph database, something like Neo4j. So you could get this graph, ingest it into a database, and then run your queries on top of the database. And this ticks a few boxes. So you could do point-in-time queries, you could do neighborhood local queries, you could do traversals, and databases are well designed for search and for updates. But they don't work well if you want to do, for instance, full graph analytics or iterative processing. For these types of queries, you may want to look into a batch graph processing system like something like Apache Giraffe, for instance, which is more optimized for iterative analytics and full graph processing. One of the issues here, as you already see, is that none of these two types of systems tick all boxes, but most importantly, none of them supports real-time continuous queries like the ones we might be interested in. In this case, we might want to look into a tool like a data stream processing system, something like Apache Flink, which, however, does not have inherent support for graph-based computation, iterations, and graph abstractions. So there is a gap here that we are trying to bridge with this project. And essentially, we are exploring whether we could bridge this gap and provide the best of all worlds. Like, can we provide both continuous and point-in-time queries, both full graph and neighborhood local access patterns, and different types of workloads on top of the same system? And to bridge this gap, we are currently looking into a new open source platform that is called Flink Stateful Functions, because it provides three very promising features that we believe could provide the foundation that we need for building these temporal analytic systems on top. The first one is an actor-like programming model. So the main idea in Flink Stateful Functions is that logic is encapsulated into functions that can ingest streams, so they can receive and send messages, and they can communicate with each other in arbitrary ways. In theory, we could build any kind of computation graph with these functions, which is nice. The second feature is decoupling between computation and state. So the idea here is that functions can define and maintain state. However, the framework makes sure that that the state management and the compute are decoupled and can be scaled independently. So the ingestion of our graph updates and the analytics on our graph state can be handled on different layers, which is nice and could help us support concurrent updates and queries. And finally, another nice feature is that these functions can be deployed either as embedded compute tasks collocated with the state for low latency, or they could be deployed remotely as lambdas. And this provides a possibility for us to design a unified interface for both ad hoc and continuous graph queries within the same system. So I have a very brief introduction to show you, what is the magic behind Flink Stateful Functions, and then I will talk a little bit about the prototype that we have built on top and some of the research challenges that we are currently facing and trying to solve. So how does this work? If you're familiar with data flow systems like Apache Flink or Apache Spark or Apache Storm, then this will be easy for you to understand. If not, I'm happy to answer any questions. But essentially, Flink Stateful Functions is a library on top of a Flink data flow, where the Flink cluster acts as a distributed database. So essentially, we have a set of Flink tasks. It's storing a partition of our state within the Flink managed state, which is RocksDB. And then Flink is responsible for delivering the messages through the data flow channels and for managing this state by checkpointing it and making sure that if something fails, we can revert to a consistent view of our state. And then, so all the messages, all the input streams flow through these Flink tasks, which look up the relevant state for a particular function, and then are responsible for invoking the compute. So they are responsible for wrapping the necessary state and the function invocation, and then triggering the compute, whether this is locally or remotely. Under the covers, this is nothing other than a streaming data flow that consists of 3 special operators. So as the streams flow in, they are first ingested by a router flat map that partitions the stream by the function address. So every function in the system has an address that is a combination of the function type and the key that is application specific. So in our case, the key could be, for example, the vertex ID in a graph. And then, so messages are routed to the right function using this partitioning. And then a dispatcher operator is a very lightweight operator that contains the definitions of the different functions in our system and is responsible for extracting the relevant state and invoking the functions. And once a function is executed, it might generate other messages which will be routed through a feedback operator and sent back into this router flat map so they can be again partitioned to the right address. So the function dispatcher operator is essentially the heavy lifter here. As I said before, Flink uses RocksDB for state management. So you can think of the dispatcher operator as a lightweight logic that runs on top of the distributed database, extracts the function type based on the message that it has received, loads the function and the relevant state, and then invokes the function locally or remotely, updates the state, and outputs any generated messages. One important thing to note here is that the way we represent the state has an implication on how many such function invocations can be active at the same time. So essentially, Flink, in order to ensure consistency of our state, only allows a single function instance being active at any point in time per key, right? So we could have multiple function instances running at the same time as long as their state touches a different key on this RocksDB instance. These functions, as I said, can be run can be deployed in different ways. One way is embedded. So this deployment option essentially packs together the function invocation and the state access within the same JVM process. This is the most performant way to run these functions, but it's not flexible. If you want to scale out your compute layer, you also have to scale out your Flink cluster, your database. Another option is to run these functions as sidecar containers that can communicate with the Flink containers via the pod local network. This is nice because now you can write your functions in different languages. They don't have necessarily to be written in Java, like Flink. And the third deployment option is running these functions completely remotely, so through an HTTP gRPC protocol, and route them through a routing service, for example, OpenShift load balancer or AWS request gateway for Lambdas, and so on. In this case, remember that functions are self-contained, so they receive copies of the state, but themselves are stateless. So their invocations have no side effects, and they can be invoked again without affecting consistency. So we have used this foundation to build a prototype system for temporal graph analytics. And this is a picture of the current state of this. So we have two input streams, one for the graph updates and one for the queries that flow through a set of predefined functions. So we have a function that is responsible for retrieving the relevant storage from the Flink cluster, a function for figuring out what type of query it is and what kind of graph view it may need. And we have implemented right now a library of different graph algorithms as functions, including connectivity, shortest paths, graph neural network inference, and PageRank. And as I said before, we can have multiple parallel invocations of these functions active at the same time. So there are a number of research challenges that we have considered since we started working on this project in January. In the interest of time, I will only very briefly discuss the graph representation, but I'm very happy to talk about any other ideas on this slide. So a very fundamental problem in this project is how do we represent a temporal graph in a key-value store, right? Our underlying database is a key-value store, so we have to somehow map this temporal graph into keys and values. Now, to ensure consistency, Flink Stateful Functions, as I said, only allows one function invocation per key, but that has an implication on how many queries we can support in concurrently, right? And there are two approaches that we have considered so far. One is, partitioning the graph and using the partition ID as the key and the partition contents as the value. And this works well for queries that look at the subgraph, because with a single lookup, we can get the entire subgraph and then all computation will be local. But then we can only have a concurrency degree limited by the number of partitions in our graph, right? So we cannot concurrently write, for example, update the state of vertex 2 and vertex 1 in this example. On the other edge of the spectrum, we could have each vertex ID being a key, in which case we have maximum consistency. But then if we want to traverse a path, let's say we want to go from 4 to 5 to 3, then this will involve 3 separate function invocations, right? So there is a trade-off there, and it would be nice if we could find a way to switch from one representation to the other based on the query requirements. Another concern with regards to storing the graph state in RocksDB is how do we actually represent the temporal neighborhood? So, somebody could say, since the vertex ID is the key, how about storing the adjacency list as the value, right? This is straightforward, it's intuitive. So in this example, this is exactly what I've done here. I have vertex 1 and the neighbors of the vertex with their timestamp stored in the value in RocksDB. This is simple, and if I get another edge to this graph, I could just go and update this list in my value. However, every read and write that goes into RocksDB means serializing and deserializing an ever-growing adjacency list. So there is an overhead here that we have to take into account. What we have done instead is to build a two-level storage, neighborhood storage, where instead of storing the entire neighborhood in a list, we actually split it into time intervals. So we have a first lookup into a map of intervals to bin IDs, and then we have a second lookup from a bin ID into the neighborhood that we are interested in, right? So temporal query that only cares about the time interval between 4 and 6, it will only need to go and deserialize, read the bin 2, right? The rest are irrelevant. So I will finish here just showing you some very preliminary results using these different storage paradigms. This is a read latency CDF for 100 concurrent connectivity queries using these different storage approaches. On the right, the green one is this naive version I showed you with the adjacency list, and the orange one is the bin interval bin approach that seems to be working much better. I will skip this one. I just want to mention that we have many ideas. We're very excited about this project. We just started exploring this space. We think there's huge potential for innovation here, and we hope to make temporal graph analytics accessible, affordable, and efficient for everyone. I would be more than happy to answer any questions you may have. And I want to mention that this is a team effort. I'm just a messenger here. Here at BU, we are a team of one PhD student, 2 master students, and myself. And we also have collaborators overseas at my alma mater at KTH in Stockholm, where we work with Professor Carbone's research group. Thank you, and happy to take any questions.
Well, that was an awesome talk. Thank you. Let's give it a few minutes if people have questions.
I was curious, since you were talking about applying this to real world problems, what you've been doing is all in one physical location, right?
Mm-hmm.
Can you say a little bit about what happens with the graphs if you have to deal with storage and computation in different locations? And
Mm-hmm. So by different locations, you mean graphs being generated at different physical locations?
right. Like if your computation and your storage is distributed among multiple data centers that are, separated by significant delay.
Yeah. So as far as I know, I don't think anybody has tried deploying Flink across data centers, or Flink stateful functions for that matter. So our assumption is that at least the distributed database, the cluster holding the state, will be centralized. So you can ingest streams and updates from different locations, but then all of them will have to end up within the same data center. It might be possible to design a cross data center storage layer, but we haven't thought about that at all. Yeah, so for now, we can just invoke the compute remotely, right?
Okay.
The storage needs to be within the Flink cluster. Yeah,
I see.
I guess if there are no more questions, well, thank you again, Vasia.
thank you. If you come up with any questions, feel free to send me an email. I'm glad to chat about this anytime.
Yeah.
Thank you.
We'll definitely have some interesting real world scenarios to talk over.
Yeah, so one thing we have been doing right now is we are collecting traces from actual microservice deployments. So we can use these real world graphs and put this into practice and see what we can find. So I think this is a very exciting use case. We'll see how that goes, and I'll update you next time. Yeah.
Awesome.
Thank you.
Thank you.
So let's move over to our next talk by Ashlyn Knox on the Fedora website revamp. So over to you, Ashlyn.
Hey, thank you very much. And thank you very much, Vasia. That was excellent. That was a really, really cool presentation. 1 second here. Okay, so yeah, my name's Ashlyn Knox, and I'm here to talk about websites. I'm a web developer with the Fedora Web and Apps team. This past summer, I also interned with the research group yourselves, but I just worked with Fedora's websites and apps and with Maureen Duffy and members of the Fedora design team on our websites. And this talk today is about us moving our website architecture over to a JAMstack and how we're using this to improve our community's quality of life as well as our web development speed. It's kind of cool listening to the last presentation because the idea of decoupling data and logic is a theme that we have consistent with what we've been doing. For our websites and our 3.0 initiative, which I'd like to talk a little bit about just to ground everyone on that, we've had a bunch of issues with our past websites over the past few decades, past decade or so, where our architectures have been challenged to maintain, the data has been difficult to update, and it's required a really high degree of knowledge in order for contributors to be able to get involved and to be able to work on the websites. This has tended to lead towards people getting burnt out really fast, it being really hard to find people to maintain them, and things like minor updates to simple static content to take a lot more time than it should. So recently with the revamp of the website and apps team, we've been looking at our websites and thinking about how we can do things a little bit differently. And over the past year with our team establishing itself and learning how to work together, we've come up with the decision to go to a JAMstack approach in which we are going to decouple our data from our presentation layer. The focus on this is static site generation. This is for security purposes and for making sure that our community members all around the world, whether they have fast internet speeds or very limited internet connections, are able to access our information. We want to be able to use modern web tooling. Our previous websites, again, they were challenging to maintain, challenging to work on. Doing very, very small changes up to larger changes required a lot more effort than is necessary. So we've been looking at modern approaches to doing web development. And the other key point of this is to reduce barriers to participation. Acknowledging that many people who would be stakeholders that maybe know more about the information that would be about one of our various editions, they wouldn't be able to directly participate in updating web pages about their edition if they didn't know the framework and the stack that we were using for our websites. Likewise, designers and other people who are building their skills technically, it was much harder for them, and myself is included in this. When I first joined on, it took quite a bit of work for me, and I'm going to talk on my personal experience with that, to be able to participate, to be able to make small updates to the sites, and to learn how to be a member of the team. And so myself and a few of the other newer developers that were joining on were like, we need to be able to approach this differently. And we worked with the more senior members of the team to look at our options, look at the constraints and requirements of our project to be able to figure out a tooling configuration that would be quick, easy, and enjoyable, and provide a foundation for us to establish better mentorship. So at the beginning of this revamp process, when we were more focused on the team revamp, we established a bunch of goals and outlines, and we carried those through to the actual website revamp phase. And the spirit of these goals is embodied in these 4 points. We need sites that are performant and secure. So from our Moin Moin wiki system to some of the lighter weight Python sites that we were building, like we did a frozen Flask site for, I think, Get Fedora and some of the others in kind of this mid stage. That was excellent because it reduced the weight of our web pages and it improved our security. So that was great. However, a lot of web developers didn't have as much experience with that particular stack. So while it worked for some of the people from Fedora's engineering teams to be able to work on our websites, it didn't make the most open place for other members of the community who are more focused on web technologies. But we learned that we need to stay secure and we need to stay fast. So with regarding our content, so the magazine, the Fedora magazine and the com blog are both managed on monolithic CMSs, a JAMstack, which we all know as WordPress. And I think this is pretty familiar to most people. And that works really well for those. However, our other websites weren't being built on WordPress. And maintaining the content on our other websites over the past number of years has been very challenging. And this has led to it not being very fun to contribute to. And this is important in order for us to be able to maintain our community of volunteers and maintain our cycle of mentorship from people coming in from Outreachy and other areas. We need to be able to create a space where people are able to grow with their skills and where people are able to have fun and learn and build cool things, because that's what building websites should be. And then we needed infrastructure that would be flexible and extendable. We're going through a growth period in our design process as well. And I see there's some members of the Fedora design team here. Shout out to you. There's some great work that's been being done the Fedora design team on improving our mockups, creating live prototyping for our web pages, and just creating a new look and feel for Fedora's websites, along with the great popularity that Fedora Linux has had over our past few releases. The way that we're presenting ourselves and presenting our information about this amazing operating system needs to be able to stand toe-to-toe with that. Thus, we need websites that can be modular and carry the flexibility and power that is Fedora. So before I get into what we've been building, I just want to make a quick comparison of a traditional JAMstack versus, which is a monolithic CMS, versus a JAMstack, which is what we're moving to. And this is a pretty standard thing. This is what I think roughly 40% of the web is built on. And in this configuration, everything is tied into each other. JAMstacks are great. They're powerful, and there is a reason why this has been a primary way for websites to be built over the past number of years. However, your data and the presentation of that data is so deeply tied into each other that to be able to migrate, to change platforms, to be able to send the information elsewhere becomes a lot of work. It also keeps developers tied to a GUI-based system for web development, which isn't a lot of fun for coders. So while that might be fantastic for people who aren't technical to be able to participate, not super great for all of us that just want to nerd out. So this is a big part of why I think these types of systems aren't what were used for Fedora's websites over the past number of years. But again, like anyone trying to migrate a site away from WordPress, Joomla, or Drupal, there's going to be a lot of work that goes into taking that and placing it somewhere else. So we are going to move to a JAMstack. And we're doing so to reduce the layers of complexity and reduce our dependencies. As we can see with that past slide, there was, let's see, how many steps were there? We got 1, 2, 3, 4, 5, 6. 6 different steps of the stack is all built into each other. For a website, we don't need this, especially for the kind of websites that we have. This isn't an e-commerce store. We're displaying basic information about a series of Linux distros, or editions of a Linux distro. Forgive me there. So we need to reduce our layers of complexity. That'll make it easier for us to be able to maintain and update our websites. And it'll make it easier for us to observe and manage security problems, which is another big problem with WordPress. I think it's pretty notorious for how many vulnerabilities WordPress has. So we don't want to be like that. JAMstack separates the data from the presentation layer. Data stored, in our case, we've stored them in YAML files, but you can store them in whichever type of file you want. You can use XML, you can use JSON data. You can actually just store your files as Markdown and publish those onto sites as well. It's kind of how you want to do it. We also, with the JAMstack, you have the choice between a Git-based workflow for your data storage or a decoupled API-based CMS such as Strapi or a headless WordPress, which is different from the traditional WordPress, or Storyblock or Sanity. There's a number of different options. Some are self-hosted, so you just have them on your own server, or you can have ones where you have it stored on their server, and the only time the data needs to be accessed from there is at build time when you're generating your static site. So here is what our JAMstack architecture looks like. So we have our headless CMS. So the logo's there. I think that first one is Strapi. I'm not familiar with the other two, but that's going to be your data. And that gets sent to your front-end system, whether it's React, Hugo, if you're into Go. We're using Vue and Nuxt, which we'll talk a little bit about the decision to do that in a few minutes. You send that to your front end, which is generated into a static site and then hosted on a build platform such as GitHub Pages. Right now we're doing our testing on GitLab Pages. Netlify is another fantastic option. But yeah, it keeps it pretty simple, pretty lean, tied nicely in with your CI/CD pipeline. So you're able to get your content out to your users quickly and without a whole bunch of effort. Plus, us being developers, we're very used to a Git-based workflow. So this is just tying the pushing of our websites to our Git-based workflow and not requiring us to have to do a whole bunch of other things in order to get those to build. And again, I made a note there, not just JavaScript. We're using a JavaScript-based generator, Nuxt and Vue. However, Hugo is a fantastic one for Go. If you're into Python, there's Pelican. If you like Ruby, you've got Jekyll. There's quite a few different options. I know Rust has a few as well, but I haven't looked at those yet. But yeah, so you have the choice of what your tooling is, and this is fantastic. I think this is particularly good for teams that are focused on doing other types of work, say like yourselves, where you're working on different types of software, which I'm not too knowledgeable about, so I'm not going to try to guesstimate at that. But you're going to be having different languages, and your websites don't need to be the main priority. You just need to get content out there. So instead of having to have someone that's specializing in managing your websites, you can build your websites using a static site generator and keep it light and simple, keep it close to the tools that you're already using. And this creates tasks that students, interns, as well as senior members, whoever else, would be able to work on without having to dedicate too much of their time to. So, and this is what's being really beneficial for us. Our productivity has increased quite a bit since we've switched to this approach to doing things, where before just maintaining and managing our sites required a lot more meeting time and a lot more discussion and issue tracking. We're able to get proof of concepts out much quicker now. So we have flexible and fast deployment, and it's been making it a lot more fun. Our community members, we see at our meetings every week how much more energy and how many more commits are happening and how quickly the pace of development has gone. So we might be focused on websites as we are the web and apps team, but this is a type of workflow that could be added to a team focused on something else and be just a small part of what they do without having to increase the labor overhead by that much. So on that, I'd just like to talk about our platform and the stack elements that we've chosen. We went with Vue.js, and the reason why we went with Vue is that it's more mature than Svelte, which is another option that's very, very similar to Vue, at least in what coding it is like. But it's more mature, so it's been around since 2014. Its syntax, when you're doing the templating, isn't unfamiliar if you're used to writing in HTML. So it's quite readable. We've been doing some training sessions with members of the design team to start working on our mentorship program and our training resources for new team members. But yeah, it's lightweight. It's got a very, very small gzip bundle, and it's got all the power that you would have with React. However, with a single file component system, your script, so your logic, in each component, the actual templating, the visible elements of that component, and then the styling, the CSS of that component is all bundled right there together, which reduces the amount of files and the complexity of the actual deployed web page. So we've been really enjoying this. It has pretty human readable syntax too, that wouldn't be unfamiliar to someone who's used to working in a language such as Python. So that's really fantastic. Along with that, we've been using Vite as our build tool, which is kind of like Webpack, but it's quicker, it's newer, it uses rollup, and it bundles very nicely with Vue as it's created by the same person who started the Vue project. So we've been using that. It comes default with our static site generator, Nuxt, which is basically, if you're into React, if you've used that before, and how React has Next.js to turn from a library into a full framework, Vue has Nuxt. You just switch the E for the U. And that's really nice. It's got a file system routing, so we don't have to do a whole bunch of work on organizing our routes. And Nuxt 3 recently came out, so it's very, very new. It's got hybrid site generation, so you get static pages, but you can also have SSR routing built into it, so you don't lose out on just being static. You get the best of both worlds, and you only have to use the weight of SSR when necessary. Likewise with the client-side routing and any client-side functionality, you have the ability to add it in when you need to, but it defaults down to your static generation to create a lightweight site. We've started using Netlify CMS, which is different from Netlify, like the deployment platform. Netlify CMS is an open source CMS that's Git-based. We tie this in with a module called Nuxt Content. So Netlify CMS just provides a front end for people who don't write code, who aren't technical, to be able to add, update, and edit our web page content, just the same you would if you were in Squarespace or WordPress. And we have complete power to configure and set up what the fields look like, how they look, and how they behave, giving us a really nice relationship between our content editors and our developers. So if the editors need something, developers can make it with just a couple changes to a config YAML file that produces the entire CMS interface. And this is actually a process we're going through right now. Maureen and I have been conducting usability tests with members of our community. So with members of the developer team, as well as members of the Fedora magazine and other stakeholders from Fedora Council and some of the other SIGs, to be able to figure out how we can improve the CMS from our initial configuration of it. Because it's so lightweight, it's so easy to change, it's not a whole bunch of effort. We're about to do a bunch of changes, and it's not going to break anything on the front end where all the work that our contributors have been put into code. They're just going to have to change some of the fields that they refer to the data in. but that's minimal compared to if you were to switch platforms of CMS platforms before. And then for a CSS, we've opted to go with Tailwind. Tailwind's a utility class CSS framework. So the reason for that being that CSS can get complicated even when it's tied in neatly with the components. Naming conventions become a little bit difficult to maintain over lots of different contributors. We all have different styles of writing CSS. Tailwind CSS just boils things down nice and neatly to utility classes. You want flexbox? Well, you give it a display. You just write class equals flex. You want to make it a flex column? You follow that up with flex-call. The naming configuration and terminology follows very, very closely with regular CSS, allowing a shallow learning curve and keeping the presentation layer of our website tightly bundled together. So during my internship this past summer, I spent some time evaluating different combinations of tooling for our websites. I looked at using React, Vanilla View to create a client-side rendered site, which I at one point had bundled with Fast API as a backend, as well as at an earlier point using Flask. The reason we went from Flask to Fast API was that Flask has a templating system built in, which we weren't going to be using. So it didn't make a whole lot of sense to continue with that, whereas Fast API is very similar to Flask, which other members of our team that are more on the Python side of things are familiar. So the idea was to give them a nice familiar backend that will be light, quick, and asynchronous that would tie to our JavaScript focused front end to be able to bring members of people that are interested in web development to the front end, because there tends to be more of an overlap there. However, we found that this required a lot more work than was necessary for what we need for our sites. So we just brought it right down to Nuxt, and we just keep it nice and tight in there. We also tried using Strapi, which is a really cool open source headless CMS. However, as it's self-deployed, which in many ways is fantastic, we didn't have the server space to be able to run it as we determined at that time. So we've opted to using a Git-based CMS because it works more closely with the information that we have. We don't need to pull stuff from too many other places. So it keeps it nice and neat there. And then we were using Bootstrap previously, which is kind of heavy and requires more learning. Like if you know Bootstrap, it's very, very comfortable, but the naming conventions are a little bit further away from vanilla CSS as opposed to Tailwind, which is why we made the move over to there. And you can see the GitLab repo down there. That's our workspace where we're testing and hardening and building out our website. So from this, we have a milestone of once we've reached templating on a number of pages and we're feeling that our components that we've designed are good, comfortable, solid. They work for the number of use cases that we've outlined in our milestone. Then we're going to be taking this configuration and moving it to a boilerplate code base that we'll use for the final deployment of these pages. And then that same code base will be able to be used for other members of Fedora that want to deploy their own web pages using our system, which will have a storybook alternative called Beatbook set up to make it so that our pages are very well documented and really easy to figure out how to work with. So where are we now? That's a lot of steps. Right now, we are still in a fairly early phase. We are creating more design mockups, and we're able to do this as we go because as our designers come up with our standards for what our cards look like, what our hero sections look like, different key page elements, which are going to be consistent across all of our websites, we're able to make those and just kind of keep rolling. We don't have to wait for entire mockups to be done to get the dev process moving. And that's another nice thing about using the frameworks that we have, is that when we create components in our fantastic open source Figma alternative Penpot, we can look at the components that we design there and make that a very clean copy into our code. And they pair very well, allowing us to move quickly. So while that's happening, we're also developing our code. So we've taken the mockups that currently exist, and we've gotten into drafting our components based off of those. And again, that sort of hardening process and getting them to be easy to use and reusable across multiple sites. And then our next phase, which is where we're coming into right away as we've finished our user tests, is just to make sure that our CMS is really easy to use, requires minimal documentation, and is intuitive and comfortable for contributors, irregardless of their technical experience. So just coming up into a quick summary here. JAMstack sites are perfect for presenting project information. It's what they excel at. Static site generation is fantastic for documentation. It's fantastic for pages that are just presenting feature lists and resources, contact pages, things like that. However, they're also great for pages or for sites that need to present the same information in multiple places, or sites that need to pull information from multiple places into them. Using a tool like Nuxt, you're able to take data from multiple different sources, different CMSs, different Git repositories, and pull that data in on Git push hooks to be able to just generate at build time. It gets built, it's live, you don't have to worry about it. And I think that I understood a little bit about what was being said in the past presentation. And this felt like it was somewhat analogous to a question that came up there about whether you can pull information from different server spaces into the same spot. And while these are for different types of software, that type of a workflow would be very easy to achieve using a JAMstack configuration. So if you have teams that are storing data in their own Git repositories in different places, instead of having to write your documentation and README in all those places and then go to a common shared space and write it again there, just have it push from when you make those first commits, have it get sent to the central spot, so you don't have to do twice as much work. And that's kind of what our main goal here is to reduce the amount of work that we have to do to be able to get even cooler websites. Thank you. Here to answer any questions that anyone might have.
Thanks, Ashlyn.
Anytime.
Can you give us an example of what it actually looks like to the end user who's contributing something who's not technical?
Yeah, for sure. It's at a pretty rough space right now, but I'll show you the version that we've just been testing.
Thanks.
Totally.
It's very exciting. I love this goal. It's like so important, especially with projects where we're involving students.
Mm-hmm. Okay, so our CMS test deploy, this is where we've been experimenting. I kind of pushed this CMS to its limits with what it's supposed to be able to do. And we found that I added a little bit of complexity that maybe we shouldn't have, but this would be our CMS's basic setup right now. So say we wanted to go into Fedora Workstation and take a look at the data for the landing page there. It's just like this. So this is just showing the assets on the right-hand side. We haven't set this up to show what the actual rendered page looks like. But on the left-hand side here, how we have it set up is that there's a couple fields for the path, the page metadata, and description. Which one of the things we'll be doing is organizing this into a metadata spot so it's a little bit clearer for people. Then we jump down here. We've got our page header. So this would be the hero section, subtitle. We're able to add any extra details, images, calls to action. And then the other sections to the page, which I can show you as well. They get broken down into these different categories. Yes, forgive the roughness of this, but we'll be leaning it out a little in the next stage. We want to just start a little bit heavier and then pare it down. But yeah, so you got your section header, and all the sections that we built previously are following the same mapping. You've got a header that can take an image and a subtitle, and then you've got a section of content where you can have a list of like information. So that's, well, let me just get that opened up. So this would be an example of one of those lists. This is that list that we're looking at right here. We got reliable, free and private, beautiful, trusted. Bang.
Neat. Wow. Yeah, that looks very easy. Wow.
Thank you.
That's amazing.
Glad you like it. Is there any other questions? Awesome. Well, feel free to get in touch with me if you're interested in any JAMstack stuff in the future, or if yeah, there's anything like this that interests you for sites for projects that you're working on.
Great. Yeah, and if you could add the link to your presentation in the notes too, that would be good, just so other people who watch this recording later on can find it and find you.
Totally. I will add that right now.
Thank you.
Sure. That's on the agenda note page, right?
Yeah, I'll put the link in here. Just a sec. Right in the Etherpad, there's a place that says insert presentation here.
Ah, fabulous. Thank you.
We'll reduce the barrier to entry for people finding it.
100%. All right, we got everybody with this link. Let's just drop it in there.
Oh, well, I'm very impressed that you came up with multiple links between these two presentations too, Ashlyn. That's great, seeing the overlap that we don't expect.
Yeah, I was surprised, like, oh, wow, this is like already being covered. Cool.
Yeah. So thank you both for coming. This is wonderful. Ahmed?
Yeah, like I said, thank you so much. And, this is just absolutely wonderful to see two talks that, when I was reading through the agenda, I was like, well, there's going to be two very contrasting talks. But then when it went through, it's like so many links between them. It's absolutely wonderful to see. So, we'll be posting the links for the slides and the videos on our website, research.redhat.com. And the next RIG meeting will be on October 4th. And the focus on that will be open hardware and FPGAs. So thank you for joining the September RIG, and looking forward to seeing you all in the next RIG meeting. Thank you.
Thank you, everybody.
Thank you.
Bye-bye.
Bye.
Bye.
Bye.